I'm really glad to have this chance to talk to you guys about my recent research on battery searching. So the title of this talk is about ab initio random structural searching of battery cathodes. It's a little bit different from the ones shown in your email, but I mean, I narrowed it a little bit down. And here's the outline of the talk. The first part I will talk about what is a lithium-ion battery, I guess, how it works, and a little bit about how cathode materials were designed historically. And then I'll be talking about the method I'm using, which is ab initio random structural searching developed by Chris. And I will use several examples to show how this kind of method will work to explore cathode materials. And in this part, there are actually two subsections. The first subsection is about, I will try to use this method to re-identify these known cathode materials, which are pretty much commercialized, especially the first two. And in the second part, I will try to do some explorative search for cheap, energy-dense, and fast-rate cathodes. So hopefully I can give you an idea. With AIRSS, we can kind of try to get new materials out of it and increase energy density of a battery. So finally, I will try to give you some insights, where we are going for. And without further ado, the first part is the background. So what is a lithium-ion battery? A lithium-ion battery is pretty simple. It's basically an energy storage device composed of three components, the cathode, the anode, and the electrolyte. So the lithium ions bind really strongly to the cathode framework. So it really likes the cathode. The energy is quite low. And on the anode side, it really binds loosely to the framework, meaning the energy is pretty high. So when you charge a battery, you basically push the lithium ions from the cathode to the anode. And when you discharge it, you just let it go. And lithium ions will go automatically from the anode to the cathode, and you will get electricity out of the circuit, and you can use your cell phone. So there are like 4 major performance metrics for a lithium-ion battery, which are energy density, rate capability, cyclic stability, and safety. So for the energy density, it pretty much just tells you how much energy you can store in a battery, and basically it reflects how many times you need to charge your phone every day. And this value can actually be calculated by multiplying the voltage and capacity. So if you think about it, the voltage essentially is just the energy difference between the anode and the cathode. So what I want to say is that from this, you can see that the cathode is quite important, because the energy density of a battery actually solely depends on the material of the cathode and anode. So the cathode is pretty important. We need to work on that. And the rate capability, it basically tells you how fast you can charge your phone and discharge your phone. And it is related to how fast lithium can move inside a battery. So one of the major bottleneck for the lithium movement in a battery is hopping inside between lattice in the cathodes, because the bottleneck is pretty small. So in this sense, we really want cathode materials with wide bottleneck channels so that lithium can pass through freely. And again, so the rate capability is really dependent on the cathode material. So cathode is important. And then the cyclic stability and safety are also related to cathode materials. I'm not going to go into too much detail of it, but just give you an idea. For some of the cathode materials, the batteries will not explode if it's under a very bad condition. But for some of the cathodes, like something containing the nickel cobalt, it will. So all the Tesla fires are coming from those kind of cathodes. So what I want to say is that the cathode really determines kind of the performance of the battery. So we really need to find for new cathode materials and which performs really well. And just in case you want to know what a cathode really looks like, here are some pictures I took like 2 years ago. So here I show you a strip. This strip is like this white. It's aluminum foil. On top of it, there are this black stuff is the particles of a cathode, and it's quite thick, like 200 microns. So when you make a battery, you just wrap this stuff up and inject some electrolyte. Boom, it's a battery. And now, before I hope that I sort of convinced you that cathode materials are kind of important in a in the battery, and we really need to find cathode materials that performs really well. So before we talk about how we use AIRSS to search for new cathodes, let's look at how people did it historically. So in the early days of in the early days of lithium battery research, people actually used titanium sulfide as a cathode, and it kind of works, but the energy density is really low because the voltage of the battery of the cathode is really low. So people dig a little bit into that and find that this is actually because the sulfur 3p band is too high in energy. So this essentially means that we cannot take too many electrons out of the system, or the sulfur will be oxidized, which is something we really don't want. So what can we do to solve this problem? So a very easy way is to substitute the sulfur to oxygen, so that we have oxygen 2p band instead of sulfur 3p band, which is lower in energy, and then we can use many of these transition metals and enable high voltages and high energy densities. So basically, from the electronic structure, we could kind of get the design principle that what we really want for cathode is a lithium stuffed transition metal oxide. But if you think about it, there are numerous kinds of lithium transition metal oxides out there. So which composition exactly you want to choose to experimental on to put in your crucible and synthesize and do electrochemical tests? That's the question. So how could we do that? So to do that, we really need to look at the crystal structures. For each composition, we have one or more polymorphs that are stable or metastable. So when we look at these structures, we can look at the diffusion channels, how wide it is, whether lithium can pass through, and how rigid the framework is. I mean, meaning that if we take lithium out, whether the structure will collapse. So basically, by looking at the structures, we can get an idea whether this will work as a cathode. But how could we look at the crystal structures? There are two ways, I guess. The first way is just to look at the structured database like ICSD. We can just go through the entries one by one, the numerous entries. I mean, it's time consuming. And the other way is to have someone really good at crystallography and really smart. I mean, Nobel Prize smart. And basically, if you give him some composition, he pretty much can guess what kind of a crystal structure will come out of it and tell you whether it's a good cathode. So both of the two methods are kind of difficult because so if you think about it, in the last 20 years of development of lithium-ion batteries, only like 4 or 5 cathode materials has been commercialized. I mean, it's really difficult. So in my opinion, the difficulty lies in 2 aspects. The first one is that the structures on many compositions has never been reported, so we cannot really look at the crystal structure database. And the second is that like many of the phases in the databases are thermodynamically stable, and actually they have been looked at. So we really need to seek for new opportunities to look for new materials. So essentially what I want to say is that what we really want is the efficient way to get both stable and metastable structures from many of the compositions that are unknown to see whether these structures are good cathode materials. So what we are doing now. So if you think about it, so this is a electronic structure discussion group. So I guess here everyone would agree the following statement, like the fast calculation of materials properties and geometry optimizations is possible, actually kind of routine today. So this kind of enable us to do ab initio crystal structure prediction. So this kind of crystal structure prediction is essentially exactly what we want. It's kind of efficient way to get stable metastable structures from a lot of compositions. So here is a crystal structure prediction method I'm using, which is called AIRSS, ab initio random structural search. So if you look at the name of it, you can get a sense how it works. Basically, random structures, or more precisely, random sensible structures, I'll talk about this later, are generated and then relax to its nearby local energy minima using ab initio DFT. For example, if you generate a random structure with like 60 carbon atoms, And if the structure is close enough to this bulky ball, like carbon 60 molecule, it will be relaxed to the structure, and then you will be able to find this molecule. Essentially, AIRSS is a method to sample the local energy minima of a potential energy surface. So I find it's easy to make an analogy with experimental synthesis to help you understand how it works. So in an AIRSS search, we basically put a different number of atoms into a cell, and we make it random. In comparison, in an experimental synthesis, we put the starting materials, essentially a lot more atoms, into the crucible, and then we raise the temperature to very high, and the material might melt or go to some disorder state. Basically, the atoms are also well mixed. So in the experiment, following that, we just cool down the material, and we at room temperature we get this resulting material, one resulting material. In comparison, in the computational AIRSS search, we get a number of different structures, and we can rank them from low to high. The structures we're interested in are the structures with low energy, and some of them are those with energy a little bit higher compared with the most stable one. So basically, I just said the ab initio random structure search. When we do the search, we basically generate random structures and do structural relaxation. But in reality, when we do real searches, we don't really generate fully random structures because that's not really efficient. So because we have this scaling law. So we know that the number of local energy minima in the potential energy surface increases exponentially with the number of atoms. So what this means is essentially we really need to constrain the search space to get efficient searching. Luckily, we have these two features of crystals. So the first one is like the atoms are never too close to each other. The second one is that if you look at the crystal structure database, most of the crystal structures that are stable have at least two symmetries. So we can use these two kinds of features to get some physical constraint on the search space, or put in the term by Chris, we can bias the search. The two types of constraint on the search space we usually use are these two: the minimal separation and the symmetry. The minimum separation is not really a single value; it's a list of distances between atoms. For example, for lithium cobalt oxide, we set the minimum distance between lithium and lithium to be 2.81, lithium oxygen to be 2.04. So we have lists. So what this minimum separation do, or MinSep do, is that it can avoid two situations. The first one is that it can actually avoid the close contact between atoms. So we know that atoms cannot be too close to each other at ambient temperature, at ambient pressure. And the other one is not really easy to think about. It's like it can actually help us to get some information on the neighbor relation. So here I give you an example. For example, if you have this copper fluoride crystal, the copper and fluorine are usually arranged in a way that is one copper, one fluorine, one copper, one fluorine. It's never like all the fluorines are crowded together to form fluorine neighbors. So if you set the fluorine minimum distance to be larger than this 1.34, like if you set it to 2.6, you will not be able to get this kind of high energy structures. You will be able to kind of only sample this kind of copper fluorine configurations. So this essentially helps you narrow the search space down. So another constraint we apply on these searches is a symmetry. So here is a picture I took from the materials project. I just randomly took some the structures or the entries on lithium metal oxides. If you look at these space groups, all of this structure except two have crystals belongs to crystal space groups with more than two symmetry. So basically, we can reject all the random structures, or we can generate structures with symmetries initially to constrain the search space. So before I give you some idea about how we can use how AIRSS works and the constraints we're using. Now, after AIRSS search, what we got are a number of different structures with different energies. How we need to look at these structures to kind of determine whether they are good cathode materials. So the way we do it is to follow these following steps. The first is that we look at this energy of these phases. We choose the ones with lower energies and put them into a phase diagram. And when we do that, we can kind of see whether this phase is on the convex hull or is above convex hull. If it is above convex hull, how high it is. If it's not really high, we can say that it's possible, kind of possible to synthesize in experiments. So if we think about it, if we think this material is worth a trial in synthesis, and then we'll go to the second step, which is we will draw a tie line between this lithium metal and this materials which we are interested in, and then we can get this kind of quasi-ternary phase diagram. From this, we can actually see the lithiation mechanism. So for cathode materials, there are two types of lithiation mechanism. The first one is the intercalation, which everyone knows. Basically, when you take the lithium out, you don't really change the framework structure. And the second route is the phase conversion route, which it means that when you take lithium out, the structure is no longer stable and will decompose into other phases. So usually the phase conversion type of reaction is lower in energy, like this one. So if we kind of find that the intercalation route is not that high in energy, we will say that it may still possible that it will take this intercalation type of reaction. So why is this important? All the materials nowadays we are using commercially are intercalation type of cathode, while the conversion are type of not that stable. It's being looked at as cathode, but it's not that stable. So in our work, we majorly look at this type of intercalation type of cathodes. So after we decide which lithiation mechanism it has, we can calculate the property of the cathode materials from ab initio calculations. Basically, we can calculate the voltage, the capacity. The voltage is basically the energy difference between the charged states and discharged state. The energy difference between the lithiated form and the delithiated form. And if we have this voltage and the capacity, we can multiply these two values to get energy density. So we have one of the most important metric from the battery, energy density, and then we can also look at the rate capability. The rate capability of battery cathode actually is related to two stuff. The first is the diffusion of lithium ions. So for that, it's pretty simple. We can just do some elastic bands calculations to look at how high is the energy barrier for lithium to diffuse in this structure. So if it's lower than 0.4, we really kind of consider it's a decent ionic conductor, and the rate might be good. Another relevant factor on the rate capability is the electron diffusion, so it's the electron transport. So it's pretty hard to directly get electron transport properties from DFT calculations, because it's especially for this kind of semiconductors, because it involves the defect levels and all these defects in these materials. And an easy way to get a rough sense on it is to calculate the band gap. So if the band gap is not that wide, we can sort of just say that this material, it has a high chance of getting kind of good electronic conductivity. So basically, from the diffusion of barrier of lithium and electronic band gap, we can kind of estimate how the rate capability of the cathode, another important factor. So the third metric of cathode performance is like the cyclic stability. It's also very difficult metric to get from pure DFT calculations, but we can still kind of get some insights from it. The way we do it is that we look at the volume change of the cathode material after we remove the lithium ions. So we remove the lithium ions and we do the structural relaxation, and then we calculate the volume change. If if the volume change is smaller than like 10%, we say it might be pretty decent. So now we've kind of built a framework to search for the cathode materials using AIRSS. I will show you some of the examples I'm using this. So first, I will show you this simple oxide, lithium cobalt oxide. So this material is what we use in our cell phones. And so during the AIRSS search, we constrain search to be conducted on 1 to 5 formula units. And we also have this kind of constraints on the search space. First, we constrain the crystal structures we generate to have 2 to 4 symmetry operations. And also we set the minimal distance between atoms using the values derived from the known structure. I will talk about it, how we can derive it if we don't know any structure. So in total, we search for like 1,200 structures for this composition. And here is the result. So the result is kind of shown in this sheaf map, which is the stochastic hyperspace embedding and projection map. It's a method developed by Ben in our group, but I'm not gonna go into detail of it, but basically each point on this graph represents one relaxed structure, and the distance between each 2 points basically reflects the structural similarity between two structures. So say if the distance between two points are very close, the structures are very similar. If they're far away, they're dissimilar. So in our search, we actually were able to find all of these different phases. For example, this triagonal layered high temperature lithium cobalt oxide phase, this is the one we use in our cell phones. And also the cubic lithiated spinel phase, the low temperature phase, which is this one. So both of these two have been experimentally confirmed. And interestingly, we are also able to find other polymorphs, especially the ones with similar to the layer structure. We find that in these layer structures, actually the cobalt oxide layer can kind of glide, can kind of flip to form different oxygen stacking. Finally, what we got from this kind of different stacking are the O3, P2, and O2 phases, like this one, this one, this one. They're very similar, just there are some shifts and movement of the cobalt layer. Apart from that, we were also able to get this kind of disorders, rock salts. So for this kind of material, the coordination of lithium and cobalt are all like 6 coordinated by oxygen, but they are arranged in a way like a rock salt, but kind of distorted, like this one, all of them except this one. These two, the I222 and FDDD, are the disordered rock salts. So basically, just I mentioned, we were able to find these low energy polymorphs of lithium cobalt oxide using AIRSS. So what I also want to say is that constraining the search space is very important to get an efficient search. So the constraints we put on the search are these two: the the minimum separation, and the symmetry. So I will show you how these constraints will affect our search using this very simple system. So here is a sheet map of the search with different constraints. So the sheet map is a little bit different from this one. So in this previous one, each point is one relaxed structure. But in this one, each circle represents one different, may represent a lot of different structures, but they are essentially the same. What I mean is that when we do this structural search, some of the structures, some of the initial structures may fall into the same local minimum, but due to the accuracy of the DFT calculations, they might have slight distortions, so they are not entirely overlapped. But in this figure, we try to put all of these same local energy minimum to the same circle. So we have the radius, which tell us the encounter rate of this local energy minimum. So from this graph, you can see that we can actually have very high encounter rate of the lowest energy structure. So with the proper the minimal separation settings. In comparison, if we don't really have this proper mean separations, if we change it to a random one, we have random minimal distance between atoms, you will see that we got a lot more structures, and most of these structures are high energy, and these results are not really what we want. And also the encounter rate of these low energy polymorphs are relatively lower. Similarly, if we set the minimum separation to be the same, instead of the random one, I mean, not a list of different mean set, but the same value, then we also get this kind of wide dispersion of local energy minimum, and the encounter rate of the low energy polymorph is still very low. So basically what I want to say is that the mean sep is very important. The minimal separation is really critical in an efficient search of the structures. So I will tell you how we can get this value from ab initio search later. So also we tried a little bit on the symmetry parameter. So without constraining the search space with symmetry, we kind of see that we can still have high encounter rate of this low energy structure. However, the computational speed is really low. It's slow, like 5-fold or 10-fold slower. So I would say that it's better we still put some symmetries on this so we can efficiently do the search. So I just mentioned that the minimal separation between atoms are a very critical parameter during our search. So in our previous search, proper mean sep were derived from the known structures. So in reality, we probably don't really know the mean sep. So how could we do that? We can actually do that by doing an additional random structural search based on random mean sep instead of a known one. So here I show you some of the results of the mean sep list I got from random structural search. You can see that for lithium cobalt oxide, when I increase the number of formula units, the relaxed structures have mean seps fast converge to a value. So the low energy side, if you look at the low energy side, the minimum separation usually kind of get to the same value. So this value actually tells you the bond length, the minimum bond length between the atoms. So if you really want to do a very safe search to search white space, you can use this value. And basically, I said that the value kind of converges very quickly with the number of formula units you put in the cell. So you can use a relatively small cell to determine this value. If you, however, in this case, we don't really use this small value because we know that the low energy structures actually has a different bond length compared with this one, the minimum one. So we just took the structures with took the minimum separation values from the low energy structures of the search. So basically, an easy way to get this kind of minimum separation is to sample with relatively small number of units, formula units, in a wide range of possible configurations, and then choose the ones that's coming from the low energy structures. So basically, I'm telling you how we can get this kind of minimal separations from ab initio calculations. Another factor to accelerate the calculations is to accelerate the DFT calculations. If you think about it, the most time-consuming step of the AIRSS search is structural relaxation during the DFT. So we better speed it up. So there's a very easy way to do that. We can just turn off some of the knobs in the DFT calculations. For example, we can turn off the spin. We can exclude the correction terms like +u. So here I show you the structural density of states I sampled from the AIRSS search with these different parameters. You can see that even with this kind of calculations with all these knobs turned off to accelerate it, the distribution is still kind of similar with the kind of high accuracy calculations. So here I plot the energy versus energy plot of these calculations. You can see that the linearity is kind of good, but there are some deviations. From these deviations, we can kind of get that we probably need to recalculate this low energy structures within the energy threshold of 150 millielectron volts per atom. So this is a way you can, this is another way we can speed up this error search just by turn off all of these knobs in DFT calculations. I guess we can pretty much get like 4 times speed up of this error search. And previously I showed you some very simple cases of this lithium cobalt oxide. The structure is simple. Now I'm showing you some structure that is a little bit more complicated. Here is a case of lithium ion phosphate. This material is a polyanion compound. So this material is kind of used in this low-speed electrical vehicles, not in Tesla. And for this search, we use the following parameters. We constrain the search to have 1 to 4 formula units, and all the searches also have these constraints on the search space, say the symmetry and the pairwise mean set. For this search, we did a little bit more on we carried a little bit more structural relaxations. In total, we have 2,300 structures. And one thing I want to emphasize is that during this search, we actually set this PO4 as unit. So when we generate this random structure, we do not have these individual atoms. We generate this PO4 as units because we know that in this structure, PO4 always forms these units to have low energy. So actually, we did some comparison for this. So if we, during the search, we do not constrain the PO4 as units, we just put them as individual atoms, the energy dispersion, the structural density of states is kind of dispersed to the high energy side, which essentially means that we are not able to get very efficient sampling of the low energy configurations. So what I want to say is that if we know any structural information on this system, we better put into the search, say, constrain the atoms into units, like PO4 units. So here is the results I show, the results for the lithium ion phosphate. So basically, we were able to find the PNMA olefins phase, which is the one we use in our batteries. And also, we were able to find this kind of high pressure CM phase. So these two phases has been confirmed by experiments. One feature you can see that these two materials, these two phases are kind of close to each other on this AIRSS search, on this sheet map, which means they're kind of similar. And there are a lot of different structures that are far away from them. So it might be interesting to look at what these structures look like. So I'll do that later. So for the third system, I would talk about this copper fluoride. So the reason I look at this material is because this material actually goes through a different reaction mechanism compared with these lithium ion phosphates, because it's a conversion type of reaction. I will talk about how we can use DFT calculations to show AIRSS search to show why it goes through this kind of conversion instead of interpolation. So for this kind of search, we really need to construct the phase diagram, because in most of the systems we know the chemistry, but if we really do something new, we don't really know the chemistries. We not only need to know the energy of this single phase, we also need to know the other phases in this composition range, so that we know whether this material will decompose into other phases. So we need the energy of all these phases within the phase diagram. So so what I want to show you is, by AIRSS search, we can actually sample this entire phase diagram to generate all these phase stabilities. So for this AIRSS, what I did was I sampled on this structure formula units, these structures. So I searched on this lithium X, copper Y, fluorine Z, and all these are constrained with a number of atoms smaller than 10, leading to 163 compositions. And for each composition, the formula units are constrained to be less than 4, and still the symmetry operations and mean set are the same with previously, except that the mean set are not derived from experimental data, but from additional AIRSS. Basically, for this AIRSS, we know nothing about this phase diagram. We start from scratch. So here I show you here is the result of the AIRSS. I mean the phase diagram constructed using the AIRSS results. You can see that this phase diagram actually is the same, pretty much the same with one I got from the materials project, except these two phases which are out of this search space. So, but I mean, still the result is pretty decent. So from this result, you can see that we can actually analyze why this copper fluoride goes through a conversion type of reaction. So as I mentioned previously, we draw a tie line between lithium and the copper fluoride, and then basically we have the stable phases along this tie line. If you see it, you will find that this copper fluoride will decompose into lithium fluoride and copper in a somewhat dynamically stable manner. However, if we really once we really force it to go through this intercalation type of reaction, it will be looking at like this. So this intercalation type of polymorph actually has high energy. Actually, the energy is like 300 billion electron volts higher than the stable one. So as the energy is very high, it will not go through this kind of reaction route. So that's the reason why the copper fluoride will not go through this kind of intercalation type of chemistry, but instead it will kind of take the phase conversion type of reaction. So pretty much from this kind of AIRSS, we can also construct this kind of phase diagram very efficiently. Now we use 3 examples to show you how we can do efficient sampling of the low energy structures of cathodes. We can also do the full phase diagram search. Now we move to something really new, the new cathode materials we're looking at. So this family of materials we are using AIRSS on are the transition metal oxalates. So why we are interested in this type of cathode material, this is because this type of material is also a polyanion crystal. So compared with others, which are the phosphates, sulfates, and silicon oxide, these materials are studied well, and the study of this material actually lead to one of the most commercial successful cathode material, lithium ion phosphate. So probably if we look at this material, we can also achieve some success. Actually, the oxalates have some nice properties for cathodes. First, the oxalate anion has a polarizability that is comparable to that of phosphates. That means that we can kind of get decent voltages from this transition metal oxalates. And at the same time, the oxalates are easily synthesized in solution-based methods, and they can be synthesized under 200 degrees Celsius. And the most exciting point that lead my research to it is because these oxalates have very interesting coordination chemistry, meaning that they can have different polymorphs for the same composition. So another 2 factors are like they are cheap, and also recently people found that the anions, these oxalate anions can actually contribute to the capacity by serving as a redox center. Usually in cathode materials, we think that the transition metal oxide, transition metal is the redox center, but in these materials, actually the anions can kind of give some electrons. This means that the capacity could be much larger. So in general, why we are interested, because this material has been overlooked, and secondly, the material is structurally complicated, which is which means that they are a good playground for AIRSS search. So we looked at it. So the structure, the composition we focus on is the lithium-2 transition metal silicate, not silicate, but I mean oxalate. So in this composition, the transition metal has 2+ oxidation states, and if we remove all the lithium from it, there might be some oxidation of the anions. So here I show you the results of the ion search, the search on the ion oxalates. So if you look at the sheet map, there are two major local energy minimum. These two local energy minimum represents the two most characteristic structures. One is the layer structure, where all the ions, lithium ions are in a layer and the anions are in another layer. The other one is a checkerboard pattern like this one. So we also put the experimental structure in this graph. You can see that these structures pretty far apart. So all these structures in between have some mixed feature of these structures. So very interestingly, we find that the layer structure actually has lower energy compared with the experimental one. So that actually essentially means there's a good chance we can make this layer structure. So another thing, if we look at the layer structures more closely, we'll find another nice feature about this is that all the lithium ions are kind of connected to each other to form a very well-connected diffusion channel. Instead, in the experimental polymorph, they need to go through this side and to another side. The diffusion might be a little bit difficult. So we calculated how easy it is to for the lithium ions to diffuse in the structures. We've actually found that in the layer structure, the diffusion barrier is like 300 some milli-electron volts, which is like half of that of the experimental found phase, meaning that this polymorph actually might be a very good high-rate cathode material, and with its good stability, it might be synthesized. And apart from this very low energy layer structure, we also find several polymorphs that have low energy but slightly higher. So here I show you all the properties I calculated as cathode material for these structures. You find that the energy density of some of the polymorphs are actually quite high. Like this layered one, the one I proposed with low energy, is like 900 watt per kilogram. It's kind of comparable to the state-of-the-art cathode materials, but bear in mind, this material is made of iron, oxygen, and lithium and carbon. This material is really cheap. So basically what I want to say is that for using this kind of AIRSS search, we can actually predict some new materials that are very promising as cathode materials. So some conclusions: AIRSS can be used to explore new cathode materials for cathodes, and by constraining the search space, we can get efficient sampling of the potential energy surface. And finally, we did some predictions that some transition metal oxalates are good cathode materials, and people in the experimental field should try to synthesize them. Finally, some future directions. So if you think about it, all the stuff I talked about are the direct search. Basically, what I mean is that we go through a lot of different crystal structures and look at their properties. It's kind of the old way, but it's a more secure way that we can get something out. A more fancy way is that if we have some structures, and then if we give it a structure and we can generate give it a property, and then we can generate structures out of the property, it's more like fancy and interesting. Now people are developing these kind of generative models on that. So this probably something we want to work on. And I mean, that's pretty much all what I want to say. So thanks goes to Chris, Ben, Bona, and David. The first two guys are in Cambridge. The other two guys are at UCL. Also the founder of this project, the Faraday Institution, and the future cat sodium. Thanks. If you have any questions, yeah.